Hello, 8th graders. So we are starting to get into our minerals unit and being able to distinguish between minerals and rocks, and then the different types of minerals that all make up rocks eventually and all that fun stuff. So here is what is going to happen. We are going to talk about mineral properties and what truly makes a mineral versus a rock, and all that kind of stuff. We're going to talk about formation and things like that, which all leads into the rock and rock cycle. So bear with me. We will get through this. So we are now working with Middle School Earth Science Standard 2-1, which states that you will develop a model to describe the cycling of Earth's materials and the flow of energy that drives this process. And we are going to emphasize on the process of melting, crystallization, weathering, deformation, and sedimentation, which act together to form minerals and rocks throughout the cycling of Earth's materials. Basically, how do we get from random little nothingnesses into something of substance? By the end of today, you should be able to list all the characteristics that provide the criteria for something to be considered a mineral and how they form. But you should also be able to list the 5 criteria for something to be considered a mineral. So make sure that you have your mineral properties notes in front of you, and get ready for whole group for sure. So, what are minerals and what are they not? Well, if science weren't already confusing enough, a mineral and rock are not the same thing. Picking up something like this is a mineral, versus if I were to go over to my bookshelf, you'd see most of those are rocks. I have like 2 minerals up there. Okay, minerals can be a rock, but a rock cannot be a mineral. So how can you tell which is which, and why is it that I can sit here and make such outrageous sort of statements? Well, we have to start by asking ourselves the right questions. Okay, so there are 5 questions you have to ask yourself in order to be able to identify a mineral, and then to start differentiating it from a rock, and then hopefully be able to actually identify the mineral in the end. So here are the 5 questions. Is it solid? Simple. Can you pick it up, and does it stay in one form? Does it have a crystalline structure? If you were to look at it, does it look like almost like a gemstone, like purposefully? Things like that. Is it formed in nature? Is it something that was made in a lab, or is this something that if you were to go outside and look in the right places, you'd be able to find it? Is it made of non-living material? Whatever is in this now, it wasn't once alive, was it? And then finally, does it have a definite chemical composition? That one's a little bit harder for me to just be able to show you, but we will get to why I can tell the difference between this mineral, sorry, I keep going the wrong direction for my camera, versus this one. Similar in shape, similar in color, but one of them is halite, one of them is calcite, and it's easy to be able to tell which one is which depending on what chemical makeups it truly is made out of. So those are the types of questions. As we progress through the rest of our PowerPoint notes and whatnot, we will be able to actually like figure out how do we ask these questions and how do we potentially answer these questions. So if you're just here for a whole group, fantastic. Make sure you remember your CHAMPS expectations as you continue on. If you're just getting here and you are starting up the rest of your independent work, keep these in mind. Let's keep moving. So is it a solid? So under normal conditions, minerals are solid. They are not liquid, they're not gas. It is in a form that you can hold in your hand, and beyond just you being clumsy, or me being clumsy, it will stay in your hand, okay? It isn't until under extreme conditions that they can turn into liquid or be dissolved within liquids. So basically, how I can tell like mercury is not a mineral is because in its normal form, it's not a solid, it's a liquid. It can bubble in your hand sort of a thing and move around and things like that. So first of all, I know it sounds really silly. You're like, gee, we're talking about the earth and minerals and rocks and things. Aren't they all solid? No, they're not, actually. But in order to be a mineral, it has to be solid. Does it have a crystalline structure? So this is an example of quartz, which this is also an example of quartz. You can't see it very well in this, but you can kind of see how it has those angled edges and whatnot. Quartz is a great example of a crystalline structure. Basically what happens is that the chemicals that make up quartz, or any other mineral, depending on which one you're looking at, the elements that make it up, once they solidify, they form this geometric pattern. If you imagine pattern blocks when you were in elementary school, like they form a specific pattern how you kind of like line them up. Elements are pure substances that cannot be broken down. So from Nova's Hunting the Elements, like we talked about how we can get down to that molecular level, but they're all made up of something. So like quartz has a good amount of silica in it, and that's what gives it this really kind of cool pillar sort of structure. So that all minerals contain one or more of the 92 elements found here on Earth's crust. Okay, there are some elements that are really only exist in like lab-based settings, but throughout the actual crust itself, 92 of them can make up our minerals. And minerals are made up of one or more of just those. No added compounds or anything like that. So crystalline structure, does it have a specific way it forms? This one, not so much, versus again, our quartz. Is it formed in nature? It cannot be produced in a lab. So there is a difference between diamonds and lab-made diamonds. Okay? Yes, they are chemically made up of the same thing. That's the only way you can make a diamond. But natural diamonds that you find in our Earth are considered a mineral still, versus a lab-made diamond would not be, because it was made in a lab. It was put under intense heat and pressure thanks to machines. So basically, was it made by the Earth and found in nature? Has it been here since the Big Bang? If it has not been here since the Big Bang, I don't want to hear about it. Okay? If it's something that had to be created through many years of different chemicals coming together, no, it's not. So minerals are considered a non-renewable resource, meaning that what is here, and once it's gone, it's gone. Is it made of non-living materials? So basically, it can't like what it is made out of. A mineral cannot be made out of something that was once alive. So it's not made up of anything that is living or once was living. So organized structure, if you think back to like what makes something living. So having an organized structure, energy requiring, meaning like it needs to take in food or sunlight to create food, response to stimuli. So as soon as you like poke at it, it doesn't move against its own volition. If you just poke a mineral, it's going to roll potentially. But yeah, capable of reproduction, growth, movement, metabolism, and death. If you answered yes to any of those, it's not a mineral. Okay. Coal and coral, coal especially, is always confused as a mineral. It is not a mineral because coal is made out of once living plant and animal, like plant and animals that have decayed and then gone through this weird process over its like non-living lifetime, to where coal is actually considered a rock, not a mineral. We'll get into that in a couple weeks though. So because it was once made up of something that was organic or once was living, coal is not a mineral. But things like sulfur or fluorite or feldspar, they are all non-living, so that's why they can be considered a mineral. Does it have a definite chemical composition? This is the one that kind of gets hard. This is where, like, if you're a chemist, yay, awesome. But we're not. I'm not. I'm really not. Okay, basically, is it made up of a definite chemical composition? Can we have a combination of elements that make up this mineral? The recipe, okay? So for halite, yeah, this is halite. For halite, the only things you're gonna find within this specimen is NaCl. And if you know anything, NaCl is salt, okay? So this does not change from sample to sample. Are you gonna have a little bit of impurities in there? Yes, but if a majority of the actual like mineral itself is NaCl, it's halite, no matter what. Now, like I have, this is a new specimen I just got. So I have this. This is also halite. If you smell it, it smells salty, okay? But as you can tell, it's much, much darker. That's because it does have impurities within it, but a majority of the specimen is NaCl. So it's only halite. So let's talk a little bit more about minerals. So more minerals are actually compounds, meaning that they're made up of two or more elements, halite, sodium, and chlorine. So that there are few minerals that are pure elements, like gold. I have a gold ring. Silver. Those are pure elements. So very few are pure. Most are compounds. Now, let's talk about different classifications of minerals. So minerals can be classified according to the type of elements that they are. So there are two different types of classifications we can give minerals, whether they are the silicate minerals or the non-silicate minerals. Now, we're so fancy in science. Silicate materials are minerals that contain a combination of mainly silicon and oxygen, and that's because those are the two main elements found in Earth's crust. Versus non-silicate materials don't contain a combination of silicon and oxygen. So far fewer non-silicates than there are silicates. So just so you're aware, silicate minerals have silicon and oxygen, non-silicate don't. And here's why. Here's the composition of our crust. So 90% of our minerals are obviously found within our crust. And that is because you can tell from here, this brown, let me give them a pointer, this brown portion of the circle is oxygen. This pinky portion is silicon, and then we go aluminum, iron, magnesium, calcium, potassium. I can't read it under my face, but yeah, so on, and then others, okay? That's what makes up our Earth's crust. Yes, you're like, but gee, oxygen is a gas. Yeah, it's trapped in all this other stuff. But oxygen makes up a majority of our Earth's crust, so what's underneath our feet. So that's why silicates are far more out there and easier to identify versus non-silicates. So non-silicates, you have like native elements. So these would be things like our metals. These are the chemical elements that may occur in nature uncombined with any other elements. So you have your metals like iron, tin, gold, silver, and mercury. You have your semi-metals, which are arsenic, bismuth, and selenium. And finally, you have your non-metals, which would be sulfur and carbon. Okay, those are all of the native elements. Then you have carbonates, so things that are mainly made out of carbon. So that would be magnesium, calcite, and dolomite. You have your halides, which have a lot of fluorite and halite have chlorine, so that your oxides have like different combinations of oxygen, but no silicon. So your corundum, your hematites, and your magnetites. You have your sulfates, so containing a lot of sulfur, but not the native element, like gypsum. And then your, if those are sulfites, I can't see it behind my head. But then you get that. I want to say that's talc. I don't 100% know. Can I put my face away? Let's pause. Can't put my face away. So, anyway, if I need to fix myself, I'll fix myself. Let's talk about the formation of minerals. So, minerals are rather easy yet super complex in how they actually form. So, minerals have to go through a crystallization. That's how we get these really pretty sort of like fluorite and quartz sort of ideas, because they crystallize in, crystallize meaning that it is the way that a mineral forms. Now, the way that typically this happens is that a bunch of elements and compounds and little bits of minerals get dissolved within a liquid. And then either from cooling or evaporation or heating, we get different types of minerals. So let's talk about that. So we have the cool solution minerals. Many minerals are actually water soluble. That's why we have mineral water. Don't pay extra money for it, please. But basically it's all these minerals that were dissolved in water, similar to like if you have a Kool-Aid pack or sugar in your lemonade, things like that. Now, this is typically ambient, meaning like just kind of the temperature it is around, not heated, not cool, sort of a thing. But ambient water that eventually evaporates over a long amount of time. The minerals are then left behind because they don't like to go up into the air. They don't turn into gases, obviously, and then allows them time to grow into mineral structures or crystals. So that would be cool solutions. Ambient water evaporated off, allowing time to form into actual crystals. Then we have hot solutions. So these are hot liquids with more dissolved solids, because you can actually put more dissolved solids in hot liquids versus cold liquids. Then the liquid is essentially boiled away to evaporate, and the solution is able to, like left over, is allowed to then turn solid and crystallize. If you've ever, like, this is the way that we get gold. Typically, that's why like we get veins of gold, because it was liquid that was once superheated and then the liquid evaporates off, leaving behind just the gold. But in a probably more like on your level sort of example, if you've ever watched or seen rock candy being made, you do a superheated solution of sugar water, you put the string in or whatever, and then over time the water evaporates, leaving behind all the sugar. Sugar is not a mineral, but it's the same process. Okay, so that this is how we get quartz and things like that. Now there is a third way of potentially forming minerals, and that is through magma. So if the rock has melted underground, the minerals have become liquefied. This is one of the few instances. But then once the magma cools, crystals are allowed to form. So this happens in things like granite and quartz and things like that. It's a much slower cooling process. So typically the crystals are much, much larger because they're given time to grow, versus faster cooling like obsidian. You get much smaller crystals. So typically this is where like the rock is melted off, but the minerals are somewhat left behind or liquefied ever so quickly, but then re-solidified just as quickly. So that's how we get minerals. Those are the different types of minerals and all that kind of fun stuff. The next lesson that we talk about, we're going to talk about how can you tell that this is feldspar without me telling you that it's feldspar, things like that. So we will get there. If you have any questions, comments, concerns, ask your teacher. And yeah, awesome. Make sure you complete your notes and you do your check-in, and we will see you soon. Thanks, everyone.